We're going to go over 5 problems about Taylor polynomials and error and introduce a couple concepts, including a confidence interval concept. Number 1, let f be the function defined by f of x equals 1 over x minus 1. What we're going to do is we're going to rewrite that as 1 over 1 plus x minus 2. And the reason we're going to do that is because the problem is asking us to write the first 4 terms and the general term of the Taylor series expansion of f about x equals 2. So this is also equivalent to 1 over 1 minus negative x minus 2. So this is essentially a geometric series where a is 1 and r is negative x minus 2. So f of x is equal to 1 minus x minus 2 plus x minus 2 squared minus x minus 2 cubed. And then the general term is negative 1 to the n minus 1 times x minus 2 to the n minus 1, assuming that we're starting with n equals 1 here. So then in letter B, it's asking us to use part A to find the natural log of x minus 1's Taylor series expansion about x equals 2. So if we notice 1 over x minus 1 or 1 over 1 plus x minus 2, if we integrate that, we end up with the natural log of x minus 1. So that means we can just integrate the Taylor series too. So what I'm going to do is I'm going to integrate the Taylor series. So if I integrate this, I'll integrate every term. And I can say that the natural log of x minus 1 is equal to x minus x minus 2 squared over 2 plus x minus 2 cubed over 3 minus x minus 2 to the 4th over 4. And the general term is negative 1 to the n minus 1 times x minus 2 to the n over n. Sorry, I forgot some plus dot dot dots. So that's part B. Now, one thing you're going to want to notice is in part B, when I integrate 1, I get x, but every other term has this x minus 2 in here. And so what I really probably want to do is write this as x minus 2 instead of just x. And the reason I can do that is when I integrate, there's always a plus c at the end. So because when I integrate with an indefinite integral, I get a plus c, I can probably want to make that c equal to 2, or negative 2, sorry, because then that will kind of make everything look nice. And then it'll make that part make sense when I make the general term. So that's something that you might want to keep in mind. Part C, use the series in part B to compute a number that differs from natural log of 3/2 by less than 0.05. So if I look at that, I'm going to notice that x is going to equal 5/2 or 2.5, because if I'm looking at the natural log of x minus 1 and I want the inside to be 3/2, I'll substitute 5/2 in. So then that means I want the remainder, when I substitute in 5/2, to be equal to x minus 2 to the n plus 1 over n plus 1, which is going to be less than 0.05. So I want this less than or equal to here for the remainder thing. So then what I'm going to do is I'm going to sub in 5/2 here. So if I sub in 5/2, that means r sub n of 5/2 is equal to 1/2 to the n plus 1 over n plus 1. And I want that to be less than 0.05. So when I do that, and I just kind of start figuring out when that equal or is less than 0.05, it's probably easiest to do one of the following two things. Just start typing this in the calculator. So repeatedly type these things into the calculator. So if n is 1, I'm going to get 2. If n is 2, I'm going to get 3, and so on. And figure out when this ends up being less than 0.05. Or you can also, in your y1, type in 1/2 to the x plus 1 over x plus 1, and then go to the table and look for when y ends up being less than 0.5. What you end up with here is we realize that this occurs at n equals 2. This is the first time that it ends up being less than 0.05. So that means that what I'm going to do is I'm going to use n equals 2. So that means I want basically this polynomial and substitute in 2.5. So the natural log of 3/2 is going to be less than 0.05 off from its actual value when I have 5/2 minus 2 minus 5/2 minus 2 squared over 2, which is 3/8. So 3/8 is less than 0.05 away from the natural log of 3/2. Problem 2. Function f has derivatives at those values. Notice that f prime of 2 equals 3. So write the third degree Taylor polynomial for f about x equals 2 and use it to approximate f of 1.5. So f of x is approximately -3 plus 5 times x minus 2 plus 3 times x minus 2 squared over 2 factorial minus 8 times x minus 2 cubed over 3 factorial. So if I substitute in 1.5, I will get -4.958. So f of 1.5 is approximately that. And again, I would probably have more derivatives in that problem. So then when I look at part B, I realize that the fourth derivative of f satisfies this inequality for all x from from 1.5 to 2. So now what we're going to do is we're going to figure out what the possible values of f of 1.5 can be, and then we're going to show that f of 1.5 can't be -5. So remember from the first part, f of 1.5 is approximately -4.958. So if we know that the absolute value of the fourth derivative of x is less than or equal to 3 for all x in the interval 1.5 to 2, then what I'm going to notice is that my R3 of 1.5, which will be the next term, the maximum derivative times x minus 2 to the fourth over 4 factorial is my remainder R3. And so I can replace m with 3 because I know that that's the maximum possible fourth derivative in the interval. And then I can replace x with 1.5, and then I just figure out that equals, and that equals 0.0078125. So because I don't know if my original was an over approximation or an under approximation, I have no idea what the next derivative is. I don't know if the next term is positive or negative in my series. Then that means I take -4.58 and I want to add and subtract the maximum error remainder, and then that gives me my confidence interval. And I'm going to add and subtract it because I don't know if it's positive or negative. So if I subtract it, I get -4.9658125. And if I add it, I get -4.95 0.01875. This is what we call a confidence interval. For f of 1.5. So I know that f of 1.5, the approximation was negative 4.958. My confidence interval is what I can guarantee f of 1.5 is between. So this is my guarantee of where f of 1.5 is. It has to be somewhere in that interval. Okay, because f of 1.5 does not have 5 in the confidence interval, then f of 1.5 cannot equal negative 5. Sorry, does not have negative 5 in the confidence interval. Then I know that f of 1.5 cannot equal negative 5. So I'm going to erase that, but that is basically the logic as to why it can't be negative 5. Problem 3 uses sixth order Maclaurin polynomial for cosine of 3x. So let's write that really quick. 1 minus 3x squared over 2 factorial plus 3x to the 4th over 4 factorial minus 3x to the 6th over 6 factorial. Now we know that this is for sure going to be an under approximation. And the reason that I know that for sure is because the next term is going to be positive 3x to the 8th over 8 factorial. And because that's the next term, and I'm going to add the next term, whatever I get for the 6th order is going to be under what the actual value of cosine of 3x is at whatever value of x we have. So what I'm going to do to approximate cosine of 0.3 is I'm going to substitute in 0.1 or 1/10 for x, and notice that this is an alternating series. So I have 1 minus 3 times 0.1 squared over 2 factorial plus 3 times 0.1 to the 4th over 4 factorial minus 3 times 0.1 to the 6th over 6 factorial. And that ends up equaling 0.9553364.875. Now, when you're doing problems like this, you're probably going to want to keep as many decimal places as you possibly can from your calculator, because we're dealing with very, very minute differences in a lot of things. So this is our approximation of cosine of 0.3. So I probably should put squiggly equal signs there, since it's definitely an approximation. Now I want to give the confidence interval and the remainder R6. So if I find R6 of x, that means I need the maximum possible derivative times 3x to the 8th over 8 factorial. The reason why I need 8 is, once again, the next term is 3x to the 8th over 8 factorial. And normally I just go n plus 1. However, cosine does not have a term that has a 7th degree. So that means I have to go to the next term and get the 8th degree. So when I substitute in 0.1 for x here, I get 1.627, and then more decimal places, but I'm not going to write them, times 10 to the minus 9th. So if I'm writing a confidence interval, since this problem is definitely an under approximation, that means I only add this value. So since this is an under approximation, this is the lower bound on my confidence interval. So 0.9553364.875 is my lower bound, and then my upper bound is going to be 0.955 3, 3, 6, 4, 8, 9, 1. And notice that I'm basically adding 0.0000. I'm not going to count how many O's, but 1, 6. I'm basically adding 16 to the last two digits here because that's what happens when it's 10 to the negative ninth with how many decimal places I have. So there's really not very much error here. Also notice that I have parentheses here because I know that this is smaller than the answer, and I know that this is bigger than the actual answer because then the term after 3x to the 8th over 8 factorial is going to subtract it again and move it back down. Whereas in a problem like this one up here, I probably actually should have made this one a parentheses, but I can't necessarily exclude this number. And the reason for that is I don't know if the derivative beyond the fourth derivative ends up being 0, and like all of the other derivatives are 0, and then that would actually be the actual answer. It doesn't give us enough information. But with cosine, I know it goes on forever, and it's not something that just ends. So that means I should probably have parentheses there. Number 4, find the partial sum of the series that's given after the first 4 terms and determine the confidence interval. Note it's an alternating series again. So the fourth partial sum, or the partial sum after the first 4 terms, it's negative 1/2 plus 1/6 minus 1/24 plus 1 over 120, and that equals negative 44 over 120, which is equal to negative 11 over 30. Really quick, think, is this an over or under approximation? This is an over approximation. And the reason why we know it is an over approximation is because the next term would be minus 1 over 720. And since the next term, which I'm going to call a sub 5, since the next term is negative, that means that negative 11 over 30 is going to be bigger than the actual answer. So then I want to subtract 1 over 720 and figure out what the smallest possible thing could be for my confidence interval, and that's going to be negative 53 over 144 if I subtract it. So my confidence interval is negative 53 over 144 to negative 11/30ths, and I don't have to add the next term because I know that this is an over approximation. Now, I also know that it's not going to be negative 53 over 144 because the term after negative 1 over 720 is going to be plus, that would be 1 over 7 factorial. So it's going to keep adding something after that, and then subtracting and adding and so on. Problem 5. Determine the degree of the Maclaurin polynomial that will approximate the value of sine of 0.3 within 0.001 of its actual value. So I need r sub n of x to be less than or equal to the maximum possible derivative of sine, cosine, whatever, and a certain power, a certain number of derivatives, times 0.3 to the n plus 1 over n plus 1. So once again, probably the easiest way to do that is going to be figuring out by typing in, oh, by the way, m is going to be 1. And we know that since it's a sine or cosine thing. So it's probably easiest to either just repeatedly type 0.3 to a certain power over that power factorial, and then I can erase them and try this to the 4th and so on, and figure out when this ends up being less than 0.001. So that's one way to do it. I can type those in the calculator. Or the other way that I can do it, once again, is go y1 equals 0.3 to the x plus 1 over x plus 1 factorial, go to the table, and then figure out what it is. Figure out when it finally ends up being less than 0.001. So if I'm looking at this and I go to the table, what I will figure out And when I say go to the table, you should probably actually type this in the calculator as I speak right now and look at the table. So actually type that in the calculator as I speak, look at the table, and figure out when it ends up being less than 0.001. So you actually know where the buttons are and you can figure it out. But what you will find is that n equals 3 works, which means that 0.3 to the 4 over 4 factorial. Oh, doggone. I forgot the factorial the whole time. Sorry. Hopefully you figured that out. But this value ends up being less than 0.001. Now, if the problem said that it has to be less than 0.0001, you have to really be careful because n equals 4 would work. So if I type in 0.3 to the 5th over 5 factorial, that is less than 0.0001. But there is also not any sign term for n equals 4. So you have to be careful. So if the problem said less than 0.0001, even though n equals 4 would work, you would have to report the answer as a 5th degree polynomial because there is no 4th degree term for sine of x. So you would need to go to the next term after that in order to get under the error that it wants. So for the problem that we actually got, since n equals 3 works, I can report the answer of 3rd degree polynomial. And that would be the degree of the Maclaurin polynomial that would approximate that within 0.001 of its actual value.